Welcome to the first video of MLOps. For better or worse, Kubernetes is going to be an important part of infrastructure going forward. There are many tutorials out there on how to use Kubernetes. I'll take a slightly different approach. I'm going to use Kubernetes to build a pipeline for parameter tuning. We'll split a large parameter grid into smaller tasks and send them to a message queue. On the other side of the queue, we'll start some workers to work on these tasks and save the results to a MongoDB database. In essence, we're going to do parameter tuning, but with hundreds of CPU cores distributed on a cluster of virtual machines instead of just one local machine. During the process, we'll use Kubernetes to deploy the message queue, the workers, and the MongoDB database. You'll get to see how Kubernetes can help you quickly and easily to deploy and manage these components. You also get to see how easy it is to scale out the number of workers, but keep in mind, this tutorial is intended to be somewhat of a showcase for Kubernetes, so it moves pretty fast. It certainly would not teach you how to use Kubernetes from the ground up. If you're interested in that, I shared a few resources that I liked in the blog post. This video will utilize Google Cloud Kubernetes service called GKE. The only reason why I picked them is because they're the most generous with their sign-up credits. For some reason, I decided to do parameter tuning across XGBoost, CatBoost, and LightGBM. Looking back, this was probably too ambitious for this small project. If you're wondering if the material in this video is production ready, they're not. In fact, writing this much infrastructure code just for parameter tuning is kind of like building your own PC from scratch. Sure, it's partly utility, but mostly you're doing it either for fun or to learn a thing or two. In total, this will be a 3-part series. In the remainder of this video, we'll dive into the details on how the training pipeline is set up and finish with a demo of the final finished working product. In the next video, we'll go over how the RabbitMQ and the worker YAML files are set up. I'll explain in details what each YAML file is doing. Finally, we'll go over the MongoDB's YAML file and the components. We'll discuss the database last because that's usually the most difficult part. I will now give a quick overview of how the pipeline is set up before jumping into the demo. It's a simple producer-consumer architecture. Essentially, we produce a list of training tasks, and then our consumer takes each task and processes them in parallel. The tasks are the parameters from the parameter grid. We'll use some code from the Jupyter Notebook to break them up into JSON messages. We'll send them to our RabbitMQ service, and our workers will connect to the same RabbitMQ service and process each message. Kubernetes will give us a simple API to increase the number of workers. As each task completes, we'll save the results to our MongoDB instance. Simple enough. Let's now take a look at how the completed product looks. So to start a demo, we'll go to the GitHub link in the blog post and clone the repo. What you see on your screen might be slightly different than what I'm showing here, since I'm still finishing up the code. We'll click on the clone or download button and copy and paste the link into our terminal. We'll do a git clone command followed by the link we copy. Once the demo is cloned, cd into the final folder. We'll do a quick ls command to make sure we have the right files. Next, we'll create a virtual environment, update pip, and install everything in the requirements.txt. Which could take a minute, so we'll just wait for it to finish. Once that's done, we'll start our Jupyter Notebook instance by using the Jupyter Notebook command. We'll start a new terminal window because we need Jupyter Notebook to run in the background. We'll cd back into our folder and open a code editor. This completes our setup stage. The first thing we need to deploy is our RabbitMQ message queue. The deployment configuration is specified in the rabbitmq.yaml file. We'll go into more details about this file in the next video. For now, let me point out 2 things. First, notice the image tag. This tells Kubernetes what Docker image to pull from the Docker Hub. Second, notice that we open 2 ports, 5672 and 15672. 15672 is a management port, where we can see the graphical user interface for RabbitMQ. We'll deploy the RabbitMQ deployment and service by using the command kubectl apply-f followed by the name of our YAML file. We can check on our deployment by issuing kubectl get deployment command or the short form kubectl get deploy. in the command line. This command shows the status of our deployment. We can check on the pods created by the deployment. Pods are a lower level resource that are often managed by the deployment resource, which is a higher level resource. If we have a pod that is not managed by the deployment, then if we accidentally killed it, or if the host machine dies, the pod goes with it. But if the pod is managed by the deployment, then the deployment will make sure that there's always Xcopy running, specified by the replica field inside the YAML file. If the host machine dies, the deployment will self-heal and schedule the pod in a different machine. We can check on the pod using the kubectl get pods or kubectl get po command. The next command we'll use is kubectl describe followed by the resource name, in our case pod or po, and followed by the pod's name. This gets us more info on the individual pod. If something is stuck in pending, describe will usually show the error message on why it is stuck. So how do we access our deployment? By default, no external traffic is allowed to connect to anything running inside of our clusters. In a production environment, we would probably expose the RabbitMQ server as an API and open it to anyone with the right credential. But for this demo, we'll use something even simpler. Kubernetes comes with a port forwarding mechanism which allows you to connect to individual pods by port forwarding local ports. This is a great debugging tool, or if you just want to get something up and running really quickly. We'll first run the kubectl get po command to get the pod's name for our RabbitMQ deployment. Then we'll use the command kubectl port forward followed by the name of our pod, followed by the ports that we want to open, which in our case is 5672 and port 15672. This will forward the traffic to localhost. Once that's done, we can open up our browser and navigate to localhost:15672 to see our RabbitMQ management UI. The username and password are both guest, G-U-E-S-T, and we can see that our node is the name of our pod, and the connection is currently 0 because we don't have any workers yet. So just like that, our RabbitMQ server is up and running. I'm going to split the terminal once again before moving on to deploying the next component. The next component we want to deploy is the worker component. What we want to do is run kubectl apply-f worker.yaml to deploy our workers. Let's now take a look at our worker.yaml file. First thing to notice is the image tag is now pointing to an image under the user YUI910616, that's me, and the Rabbit worker image is built using the source code in the worker folder. Second, for the workers, we have specified the number of CPU and memory requests. Each worker is limited to 1 CPU and 750 megabytes of memory. And lastly, we noticed that there are 3 replicas, whereas the RabbitMQ server we only have 1. This means that we'll have 3 different workers deployed into our cluster. Next, let's run the kubectl get deploy command to see our new deployment, and then run kubectl get po to check if the new pods are already running. We can flip back to our browser and see that in the RabbitMQ UI that we now have 3 workers connected to our queue. We'll type in a new command called kubectl logs -f followed by the name of our pod into the shell to stream the output into our terminal. This will output any print or log statements from our Python code. We can see that the first print statement is waiting for messages. To exit, press Ctrl+C. And this comes from our source code, which is stored in the workers folder in the file workers.py. Finally, for the database, I'm going to split my terminal again and then run kubectl apply-f, this time with the mongodb.yaml file, to deploy our database. The YAML file for deploying a database is a lot more complicated, and we'll go over it in the last video. We can use kubectl get rs to check on our replica set status. We have replica set this time instead of a deployment, and deployment would also work in this instance. Once we see that our MongoDB deployment is up and ready, we'll do another port forwarding. This time, we'll use the pod of the MongoDB deployment and using the port 27017. Once the port forwarding is completed, we can connect to it by opening up Compass and connect to MongoDB //localhost 27017. As you can see right here, once our connection is established, it'll open up a graphical user interface to our empty MongoDB database. Now with all 4 components finally all deployed, we can now return to our Jupyter Notebook. Inside our Jupyter Notebook, we'll execute the first cell, which just imports the necessary packages. In the second cell, we have a list of 3 dictionaries. Each is a parameter grid for a specific package: XGBoost, LightGBM, and CatBoost. We also have a split params function that takes the parameter grid and splits them into n jobs. Once we execute the second cell, we should see an output telling us the total number of parameters, the number of parameters inside each job, and the number of jobs. For this demo, we have about 26,000 parameters to search through, and they're divided to about 5,000 jobs, with each job containing about 6 parameters. The next cell will show us what the first message looks like. You can see that it's just a list of strings, and the strings represent a JSON message, and each JSON message is a parameter. Finally, in the last cell, we use a package named Pika to send the jobs to our RabbitMQ deployment. Switching back to our management UI, we see that now we have 5,000 jobs waiting to be completed, and we have 3 workers working hard to complete these jobs. As the jobs finish, we can switch back to Compass, and we should start seeing the results roll into our MongoDB database. Now for the final magical moment, what if we wanted to increase the number of our workers? With one simple command, we can do that. The command is kubectl scale -- replicas with the number of the desired replicas, and then the name of your deployment. We can use the commands like kubectl get deploy and kubectl get PO to see if the command worked. As you can see from my screen, the desired number of workers replicas is now increased to 40. Many of them are currently being created. You can also see that as the number of workers finish creating, the number of connections inside of our RabbitMQ UI, which shows the number of workers connected, is also going to increase. This shows that the workers are created successfully and are connected to our RabbitMQ server. Now you might be wondering, what happens if we run out of CPU? After all, each worker requires 1 CPU to run. We can take a look and see how our computing resource is doing by using the command kubectl get node. Once we have the name of our node, we can use something like kubectl describe followed by the word node and followed by the name of our pod to check if all the CPU and resource memories are depleted. Looking at this particular node, we see that we have pretty much maxed out all of our resources, but if we scroll up a little bit, we can also see the number of CPUs and the number of RAM that this particular VM has, and is limited to 32, which means we can at most deploy about 32 workers. So it's not going to get us all the way up to 40. If we need more computing resources, we can use a GCP command to ask for more computing resources by increasing the number of our node pool. This is just going to give us more virtual machines. The command is gcloud containers clusters resize followed by the name of your project, followed by --null-pool, followed by the name of the pool, and followed by the number of nodes that you want. I'm going to resize ours to 4. This will again enable us to increase the number of our workers. Remember that each worker is using about 1 CPUs, and now that we have about 4 nodes each containing 32 CPUs, we have about 120, 130 CPUs. So let's increase our number of workers to 120. This means we now have 120 CPU cores doing the parameter tuning for us. Essentially, we can keep scaling out the number of machines and the number of workers to however many CPU cores you want, just limited to however much money you have. So this is how we scale our parameter tuning to hundreds of CPU cores using Kubernetes and a lot of infrastructure code. This completes our first video. In the next video, we'll dive into details about each YAML file and what they do, and deploying most parts of the pipeline to the cloud except for the database.